So let's continue with the discussion of eigenvalues and eigenvectors. This time, let us begin with an example where there are complex eigenvalues. So let us straight away learn how to deal with complex eigenvalues. So let us take a very simple example of a 2 by 2 matrix 1, 2, minus 2, 1. Matrix is real, and let's calculate the characteristic equation determinant of xi minus a. Turns out that it's going to be x minus 1 the whole squared plus 4, that is x squared minus 2x plus 5, or the eigenvalues are 1 plus minus 2i. Let us take the eigenvalue 1 plus 2i and see what happens. Lambda is 1 plus 2i. We have to solve a minus 1 plus 2i into capital I, x equal to 0. We need a non-zero x. Okay, so let us write down this matrix properly. So I have to subtract off a 1 plus 2i from the diagonal. It will be minus 2i down the diagonal and 2 and minus 2. Obviously, we all notice that R2 is minus I times R1. R2 is minus I times R1. And so the second row can be made 0 through a row operation. And we are left with only the first equation. And then we can divide by 2. And we got minus ix1 plus x2 equal to 0. There is one free variable. And the general solution is t and it. And we need an eigenvector. So t must be non-zero. And so I can take t to be conveniently 1. And 1i is an eigenvector. Exercise, take the other eigenvalue and then do the same thing and find the other 1 minus 2i and find the corresponding eigenvector. Remember, again, I'm flagging it. Eigenvector is not the zero vector. Eigenvector cannot be 0. Eigenvalue can be 0. So don't say that, oh, I solved the system of equations and I got 0, 0, 0 as a solution. Now let us come to the nature of the characteristic equation. Now let us write the characteristic equation as determinant of xi minus a equal to 0. I mean, idea of taking xi minus a rather than a minus xi is because the leading coefficient will become 1. It becomes a monic polynomial. A polynomial whose leading coefficient is 1 is called a monic polynomial. So if I write it like this, the characteristic polynomial becomes a monic polynomial. So what are the monic polynomial? So determinant of xi minus a is x to the power. It's an nth degree polynomial, so it will be x to the power n, monic. So leading coefficient is 1 plus c1 times x to the power n minus 1 plus dot 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 plus cn. So these are the coefficients. Now let us put x equal to 0 straight away. We get cn, right? When I put x equal to 0, I get straight away cn equal to minus 1 to the power n times determinant of a. So the constant coefficient in the characteristic equation, characteristic polynomial, has been computed. What are the previous term? Cn minus 1 x. No? The coefficient of x. The coefficient of x is cn minus 1, and I want the coefficient of x. So one way to get the coefficient of x is to differentiate both sides of star with respect to x and then put x equal to 0. The constant will first disappear. Cn minus 1x, when I differentiate, I'll get x. And the others are quadratic, cubic terms, etc. When I differentiate, there'll be x remaining, and that will disappear when I put x equal to 0. So I must differentiate. So now differentiating star with respect to x and putting x equal to 0, cn minus 1, there's a typo here, cn minus 1 equal to ddx of determinant of xi minus a at x equal to 0. At x equal to 0. And you need to recall how to differentiate a determinant. How to differentiate a determinant? Suppose, for example, I got a determinant like this. A11, A12, A13, A21, A22, A23, A31, A32, A33. How do I differentiate determinant? Differentiate the first column, keep the other two columns intact. That get one determinant. And then differentiate the second column, keep the first two columns intact. That's D2. Differentiate the third column, keep the first two intact. That is D3. So the derivative is the sum of three determinants. So that's the way you differentiate a determinant. So when you differentiate it, you have to differentiate determinant of xi minus a each time you'll differentiate one column and keeping the other two columns intact. So what will happen when you do it here? So when you do it here, you will differentiate the jth column, keeping the other columns intact. When you differentiate the jth column, after that you have to put x equal to 0. Remember? After differentiating, you have to put x equal to 0. You have to calculate dj of 0. But dj of 0 will have the jth column xi minus a. So when you differentiate the jth column, there is a x in the jth entry, and all the other entries are constant. So when you differentiate, the jth column will simply becomes ej cap. Once the jth column becomes ej cap, I'll expand using the jth column, obviously. So let us do it for the first column. The first column, what will it be? It will be 1 0 0 0 0 0. That's all, and the other columns are kept intact. So what is D10? It will be the minor M11. Similarly, D20 will be the minor M22. The minor obtained by deleting the first and the second, the minor corresponding to A11. And what is D2 of 0? It will be the minor corresponding to A22. That will be M22. So the derivative, it will be ddx of determinant of xi minus a at x equal to 0 will be d10 plus d20 plus dot 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 plus dn of 0. That will be the sum of the n minus 1 by n minus 1 subdeterminants of minus a, or the subdeterminants of minus a. And so what happens is that you will get the they are called the principal minors. Minus a because it is minus a because xi minus a it is. With xi minus a. So what is going to happen? Is going to be the sum of the n minus 1 by n minus 1 principal minors. These are called the principal m11, m22, mnn are called the principal minors, and their sum is called the sum of the n minus 1 by n minus 1 principal minors, and that is going to be the coefficient. Of course, there's going to be a minus 1 to the power n minus 1 because we're going to do it not with a but with minus a. Remember, because the equation, because it is xi minus a. It is xi minus a, so there'll be a minus sign. Okay, so maybe I should put a minus sign here also. I'll get that. I'll do these changes, and I will when I share with you the slide. So what are the coefficient of? So what are the coefficient of the x in the characteristic equation? Coefficient of x in the characteristic equation is minus 1 to the power n minus 1 times the sum of the n minus 1 by n minus 1 principal minors of a. Okay, what is the coefficient of x squared? Coefficient of x squared is 1 upon 2. We have to differentiate this equation. We have to differentiate this equation now twice. There's a Cn that will disappear when one's differentiation. Cn minus 1x that will differentiate when I do the 2 differentiation. Cn minus 2x squared. When I differentiate it twice, I'm going to get 2 factorial times Cn minus 2. And then cubic 4th degree, when I differentiate it twice and then put x equal to 0, it's going to disappear. X cube, x to the power 4, etc. will disappear after 2 differentiations followed by x equal to 0. And so what is your Cn minus 2? Cn minus 2 is going to be 1 upon 2 factorial. Yes, it's going to be 1 upon 2 factorial times d2 by dx squared determinant of xi minus a. Okay, so now let dij with the determinant obtained by differentiating the ith and the jth column once, keeping all other columns intact. Now, if I take that same column and I differentiate it twice, I'm obviously going to get 0. And other thing is that dij0 is the same as dji0. Now, so when I do the two, when I want to differentiate the determinant twice, what do? You first differentiate the determinant once. You'll get d1 plus d2 plus dot 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 plus dn, where di is obtained by differentiating the ith column once, keeping all other columns intact. Now I must differentiate di. When I differentiate di, I'm going to each of these n determinants has to be differentiated again. So each of them is going to give me n determinants. So totally I'm going to get n squared determinants. So di I have to differentiate. I'll get n determinants, and I have to differentiate each column of di. That means that I differentiate the ith column and jth column once. So that's how I get. So The second derivative is summation dij. And I have to put x equal to 0 after doing that, performing the differentiation. And I have to add them up, and I have to divide by 2 factorial. You have to do this algebra. All this algebra has to be done. So now I differentiate two of the columns, and I'm going to get the n minus 2 by n minus 2 principal minor of minus a. You should do it. Actually, take a 4 by 4 determinant and do this. Calculate xi minus a, differentiate it. Take the first column and the third column, for example. Differentiate, compute D130. Compute D130 and check what 2 by 2 submatrix you get. So keep doing this and you will realize that so you'll get the Dij0 will be the n minus 2 by n minus 2 principal minor of minus a, or minus 1 to the power n minus 2 times n minus 2 by n minus 2 principal minor of a. How do I get this principal minor? Delete the ith row, ith column, jth row, jth column. That's how you get the principal minors. So the second derivative is 2 times, because dij is the same as dji, I can write it as 2 times summation dij 0 I less than j. So coefficient of, so when I divide by 2 factorial, the coefficient of x squared is minus 1 to the power n minus 2 times the sum of the 2 by 2 n minus 2 by n minus 2 principal minors of a. A little thought will now convince you that the coefficient of x3, x cube, the coefficient of x cube is minus 1 to the power n minus 3 times the sum of the n minus 3 by n minus 3 principal minors of a. And so it goes. And how do you prove this? You have to differentiate the determinant 3 times. So you'll get n cube determinants, dijk. And then after differentiating, you have to put x equal to 0. And then you have to sum it. And when I differentiate the same column twice, it's going to be 0 anyway. So the only way you're going to get anything non-zero is I, j, k are all different, pairwise different. And there'll be 6 permutations. And then you have to divide by 1 upon 3 factorial. So please think over. I mean, it's routine. Once you get the hang of it, you know what to do, and it's a matrix routine. And you'll be able to figure it out. So let us write this out for a 3 by 3 case. So the characteristic polynomial of a 3 by 3 matrix is going to be x cube minus the coefficient of x is minus 1 to the power 3 times coefficient of the constant coefficient is minus 1 cube times the determinant. Coefficient of x is sum of the 2 by 2 principal minors, and then coefficient of x squared is sum of the 1 by 1 principal minors. Okay, sum of the 1 by 1 principal minors is a11, a22, a33. It's simply the trace. So it's x cube minus trace of a times x squared plus sum of the 2 by 2 principal minors times x minus the 3 by, there's only one 3 by 3 principal minor, namely the determinant itself. So let us use this to compute the characteristic polynomial of this minus 1, 2, 1, 1, 1, 0, 0, 2, minus 1. Okay, what is the trace? Trace is the sum of the diagonal entries, it's minus 1. For the determinant, compute the determinant directly using the first column. It's minus 1 times minus 1 minus 1 times whatever, minus 2, and then the third one anyway is 0. You get 5. Now you have to calculate the 2 by 2 subdeterminants, a11, a12, a21, a22, the principal minors. A11, the diagonal of the principal minor is a part of the main diagonal. A11, A1, A11, A22, A11, A33, A22, A33, A1, and then you calculate these 3 2 by 2 principal minors. Their values are minus 3, 1, and minus 1, and their sum is minus 3. So x cube minus trace. Trace is minus 1, so x cube plus x squared plus sum of the 2 by 2 principal minors, which is minus 3, so minus 3x, and then the determinant. It should be minus 5. Sorry, it should be minus 5. The determinant is 5, so the last term is minus 5. Okay, so sum of the eigenvalues is a trace of the matrix. The product of the eigenvalues is the determinant of the matrix. Okay, so let lambda 1, lambda 2, lambda n are the eigenvalues. They are the roots of the characteristic equation. So lambda 1, lambda 2, lambda 2, lambda 3, lambda 3, lambda 1, etc., etc. Take two eigenvalues and take the products and then take the sum. Sum of the products of eigenvalues taken two at a time. What is that going to be? The coefficient of x to the power n minus 2. And that's going to be the sum of the 2 by 2 principal values. Okay. So let P be a polynomial of degree n, and then let the roots be lambda 1, lambda 2, lambda n. Then lambda 1 plus lambda 2 plus lambda n is sum of the roots is minus c1. Sum of the roots taken two at a time is c2. Sum of the products of the roots taken two at a time is c2. Sum of the products of the roots taken three at a time is minus c3, etc. And so that's how we get. And then from this, for the characteristic equation, we know what is c1, c2, cn, and then the result follows. Okay. Okay. If A is a real matrix, then complex roots will appear in complex eigenvalues, if any, must appear in conjugate pairs, and this is an often useful fact in calculations. Okay. Now suppose if A is a matrix with eigenvalues lambda 1, lambda 2, lambda n, the eigenvalues are the roots of the characteristic equation, and their roots may be repeated. The characteristic equation could be lambda x minus 1 cubed into x plus 2 squared, in which case you should write it as 1, 1, 1, minus 2, minus 2. That's what counted with multiplicities mean. Now, if A is a matrix and I know the eigenvalues of A, I want to know the eigenvalues of A squared. I want to know the eigenvalues of A cubed. What are they? Simple. Very simple. If lambda 1, lambda 2, lambda n are the eigenvalues of A, then what are the eigenvalues of A squared? Lambda 1 squared, lambda 2 squared, lambda n squared. What are the eigenvalues of A cubed? Lambda 1 cubed, lambda 2 cubed, lambda n cubed. What is the eigenvalue of A squared minus A? Lambda 1 squared minus lambda 1, lambda 2 squared minus lambda 2, lambda n squared minus lambda n. More generally, if GA is a polynomial in A, for example, GA could be A squared minus 3A plus 2I, for example, or Gx could be x squared minus 2x minus 3, then G of A is A squared minus 2A minus 3I. Then what are the eigenvalues of this new matrix GA? It is simply G lambda 1, G lambda 2, G lambda n. Is a list of eigenvalues of GA. And so what is the determinant of GA? Determinant of GA is simply the product of the eigenvalues. Remember? G lambda 1, G lambda 2, G lambda n. The proof of this theorem cannot be done here. The proof is not difficult when the eigenvalues are distinct. When these lambdas are all distinct, it's not difficult to prove this. But the proof becomes, but when the eigenvalues are not distinct and the argument becomes more subtle, and we cannot discuss this here. We can do this in the MA401 course or the higher level linear algebra course. When the eigenvalues are distinct, one can use some argument using Cayley-Hamilton theorem, etc., to prove it. But the general case requires a perturbation argument. Okay, so you can take it on faith. You can take this theorem on faith. So if you have the list of eigenvalues of A, it's very easy to know the eigenvalues of I plus A squared. Take a new matrix, identity plus A squared. What are the eigenvalues? 1 plus lambda squared, 1 plus lambda 1 squared, 1 plus lambda 2 squared, 1 plus lambda n squared. You can do that. All right. So let us take an example. 3 by 3 skew-symmetric matrix. Well, one of the eigenvalues must be 0. Remember, determinant of A is 0. The matrix has a nullity, and so there is an element in the null space. So 0 is an eigenvalue. So 0 is an eigenvalue. But we know that the sum of the eigenvalues is a trace. What is the trace of the matrix? 0. And first eigenvalue is 0. Lambda 1 is 0. So we get that the other two eigenvalues are lambda 2 and lambda 3. So lambda 2 plus lambda 3 is 0. Fine. What is the sum of the 2 by 2 principal? What is lambda 1, lambda 2 plus lambda 2, lambda 3 plus lambda 3, lambda 1? The sum of the 2 by 2 principal minors. What are the 2 by 2 principal minors? 0, A minus A0. What is the determinant? A squared. What about this 2 by 2 principal minus 0, C minus C0, C squared? What about 0, B minus B0? The determinant is B squared. Sum of the 2 by 2 principal minus is a squared plus b squared plus c squared. So lambda 2 lambda 3 is a squared plus b squared plus c squared. But lambda 3 is minus lambda 2, remember? So minus lambda 2 squared is a squared plus b squared plus c squared. So lambda 2 is I times square root of a squared plus b squared plus c squared. And lambda 3 is minus I times square root of a squared plus b squared plus c squared. Complex roots appearing in conjugate pairs, as you see. We shall see that the eigenvalues of any skew-symmetric matrix are either 0 or purely imaginary, and we have proved it for the 3 by 3 case. Now let us go back to the problem which we started in the previous chapter. A is a skew-symmetric matrix. Remember? There I called it lambda. I took a 3 by 3 skew-symmetric matrix. I called it there lambda. And I want you to calculate determinant of I plus a squared. Compute the determinant of I plus a squared. Remember? That was the that was the place where we got stuck. We were doing it when we were doing the block matrices, determinant of block matrices, etc. There we came across this problem. Now we are able to solve it. So we know the eigenvalues of A. What are the eigenvalues of A? 0 plus minus I square root of a squared plus b squared plus c squared. So what is the determinant of I plus a squared? What is the polynomial? 1 plus x squared. What are the corresponding eigenvalues? 1 plus lambda squared. What are the lambdas? 0 plus minus I root a squared plus b squared plus c. So what is 1 plus lambda squared? 1 minus a squared plus b squared plus c squared, counted twice. So these are the 3 eigenvalues. So what is the product of the eigenvalues? The product of the eigenvalues is 1 minus a squared minus b squared minus c squared, the whole square. The determinant has been computed. So in the previous chapter, we have to stop short of doing this, and I said that we will continue the calculation after we develop the theory. So this is the now we have completed this particular aspect of it. I think I'll stop this lecture here, and I'll continue. The next topic is on diagonalizability, and we will take it up in the third capsule.